right? So now we know how to find the displacement in the x direction because we know our initial position and we know our final position. Just take away these vectors. We can find our displacement because we know this and we know this. We can find our displacement in the y direction because we know our y final and our y initial. And if we know our initial velocity, we may not know it, but because of the last experiment, which was to calculate the initial velocity, now that we know that, all we need to know is the angle of launch to find our respective components. Initial velocity in the y direction, which is just v naught sine theta, and the initial velocity in the x direction, which is just v naught cosine theta. Our time of flight will be calculated from, well, we could talk about the time in 1 second, okay? Let's evaluate the accelerations. The acceleration in the x direction is going to be negligible, which means that it's going to be 0. So that means that this entire piece here is just going to go to 0. So we're just going to let that equal to 0 since acceleration is 0. Acceleration in the y direction is going to be a negative g. So that means that instead of having a sub y here, we're going to replace it with a negative g, and subsequently the plus sign will change to a minus sign. So we're going to rewrite these equations accordingly. xf, or the displacement in the x direction, is just equal to the initial velocity in the x direction times the time of flight. That's it. That's our equation of, that's our initial equation. What we want to do is we want to be able to predict our y. And then you have our y displacement. It's equal to the initial velocity times sine of the angle times t minus 1/2 gt squared. All right. So now that we have this equation, we're going to use equation number 2 to solve for time. Notice that the equation is just quadratic in time. Equals to 0. So if I say that it's quadratic in time, that just means that this piece is a coefficient, this piece is a coefficient, and this piece is a coefficient, okay, of time. And so if I want time, I can just let this coefficient equal to A, this coefficient equal to B, and this coefficient equal to C. And the solution to this equation would be a negative b plus or minus square root of b squared minus 4ac all over 2a. So all we have to do is just substitute those numbers into this and we can get 2 solutions. We want the positive time solution since the negative time solution is indicative of us looking backwards and not forwards from a point of launch, okay? This is pretty much the theory. We're going to utilize a couple of equations. We're going to utilize equation number 1 to predict the range, and we're going to utilize equation number, and I didn't even give it an equation, but let's call it equation number 3. And utilize equation number 3 to calculate the time. So provided we know our initial velocity, which is what we calculated last time, our angle of launch, which is going to be 20 degrees, and our time of flight, which is just going to come from here. Okay, like that, which is going to come from here. Then we can predict the range. And that is where we want to stop, at predicting the range. Okay, so this is the theory. And I will share these notes with you. I'll probably put them in this section, okay, as opposed to the lecture notes, since it's, even though it's a lecture, it's like before the lecture, and all of the other lecture notes are like produced really quickly. So I'm going to stop here. In the next video, we're going to go ahead and take those. We're going to start doing the experiment. All of this theory is in your Excel spreadsheet.